It was a very nice challenge to do this presentation at this time. Let's see how it goes. And first of all, I'm going to start. Are you seeing the screen? Okay, now, Anna? Yeah. So I'm telling where I am. I'm at the Algarve at Faro, on the southernmost part of Europe. And our university, the University of Algarve, is quite small one, but very much devoted to marine science. And it's really easy to understand why. The university is located just there. This is one of the campus, of the two main campus of the university. My house is there. The airport, international airport, is 500 meters from my house. And the beach is just another 1 kilometer away, and just 3-4 kilometers away from the university. So this is really easy for us to go to the field, to have a natural laboratory. This is a very nice Barry Island system with 60 kilometers long, a lot of salt marshes, a lot of biodiversity, also interesting economical and social issues. And then we have another incredible coast, including pocket beaches on the west coast and also on the southwest coast, with both high energy coast here on the west coast and a little bit lower moderate energy coast on the southern one. So this one is completely exposed to the Atlantic, and this one is just exposed to the Gulf of Cadiz. So we have a lot of diversity in such a small place. And we have a university with a natural lab just nearby, so we profit. And that's why here we have a lot of people working with marine issues. Okay, going to the presentation today. Well, the title is Assessment of Risk Reductions Measures to Minimize Impacts of Storms at Sandy Shores. And this is, of course, not the work of just one person, and that's why I have here the entire risk team with myself. risc-kit is, it was a project, a European project that already ended 3 years ago, but we are still having results from this project, and most of that, more than that, it gave us tools that can be used and applied, and they have been used and applied for minimizing the risk at coastal areas. So I'll present results from the team, and mostly the team of the Algarve. I present some new stuff that we have been developing after the project, but a lot of it comes from the original risc-kit project. Well, I'm starting with the introduction, motivation. Of course, all of you are fully aware of the consequences of storms. Just to keep in mind, we have here in the center Katrina, and Katrina and Sandy were two major storms in the States with devastating consequences. On the left, we have image of Xynthia. Xynthia crossed Portugal and then arrived to France. It had a lot of consequences in the Algarve because the track was from south to north. But the most of the consequences were in France, more or less on this region, killing about 60 persons during the night by flooding. And we also had in 2014 another major storm, Hercules, which is considered the storm with the highest power in the last 100 years on the west coast of Europe. And we have here a very nice image of the Hercules overtopping just near Lisbon on the west coast of Portugal. So we know that we have high impact, strong coastal risk, loss of life, unfortunately, in several cases. And so this is a huge motivation to know more and a huge motivation to define methods to reduce the risk at coastal areas. Well, this is going to be worse in the future. And this is going to be worse in the future because risk is the multiplication of the probability of hazard by the consequence. And of course, we're going to have an increase in hazard in association to climate change. We're going to have an increase in hazard in association with storminess changes and also sea level rise, which will increase extreme sea levels. Even in areas like Portugal and the Algarve in particular, where we do not expect changes on storminess, so we do not expect here for our coast that wave heights will get bigger. We do have sea level rise, of course, and thus extreme sea levels will increase. For instance, getting this quotation from Michalis Vodouskas, there is expected an increased global average 100-year extreme sea levels between 58 and 172 centimeters for so we're going to have increased extreme sea levels in the future. This will increase the probability of hazard. And of course, we also have the other part of the risk equation, which is the consequences. And the consequences are also potentially increasing around the world, mainly because increasing on exposure. This is particularly true for the countries under development at this area, at this time, that are increasing their occupation of coastal areas. But even in areas where coastal development is supposedly not increasing at the time, like in our coast, our management plans supposedly do not allow us to build much more near the coast. We are still increasing the economic value of those areas because we are, for instance, transforming former houses into hotels. We are transforming low values building in high value building. And so we are also increasing the consequences because we are increasing the economic value and even the potential of loss of life. So this part of the equation will also be increasing in the future. So both of them, both of parts of the equation of risk will be increasing on the future. One of those directly related with climate change, the other directly related with the occupation of coastal areas by us. Some indications from again a work from Michalis. These are values for Europe, and what is stated is that without further investments in coastal adaptation, it is expected a rise up in 2 to 3 orders of magnitude on the expected annual damage. So the expected annual damage by coastal flooding and erosion is on the order of 1.25 billion euros at this moment, and it is expected to rise up by the end of the century to something between 100 and 1,000 billion euros, of course, without coastal adaptation. The current expected annual number of people exposed to coastal flooding in Europe is about 100,000 people, and I think this number is small if we take in consideration just Venice, for instance. This is probably a low number. It is projected to increase by the end of the century to 1.5 to 3.7 million of people that can be exposed to flood every year in Europe. Of course, these values are without any sort of adaptation. I don't think they will happen, in fact, because we'll need to do adaptation and we'll need to do any sort of coastal management, of course, to avoid these values to be true by the end. And there is, of course, what is the most important on this talk is how to assess risk and how to test disaster risk reduction measures in order to do this coastal adaptation in the most effective way. So we can do that by implementing disaster risk reduction measures at models and then to simulate their response, including climate change scenarios. So with that, we can evaluate the disaster risk reduction measures, and we can assess their effectiveness and choose the optimal ones. At the risc-kit project, that was a little bit what was done. The risc-kit developed methods, tools, and also management approaches to increase coastal resilience and to reduce coastal risk. Two main, there was 4 or 5 tools that have been developed. One of them was called Early Warning and Decision Support System for use on hotspots. So after knowing what are the main hotspots on a coastal area, detailed models have been used to define an early warning system. I'm not so much here talking about the early warning system, but more on the decision support system. So how to use these models to have a decision support system that can be positive for coastal managers, for instance. So the main goals of my presentation will be to present approaches to test risk reduction measures and their effectiveness in minimizing the impacts of coastal storms. And then I will show some case studies, some application for storms at Faro Beach. So the beach I just have been showing at the beginning of the presentation. Let's start with the modeling of the impact of coastal storms. I'm not going in detail on the models, but much more on how to use them, let's say. This is mostly done nowadays by using model trains, connecting hydrodynamic and morphodynamic modeling that at the end calculate the hazard. So we have, for instance, a large scale wave propagation model that then goes towards an inundation model or a coastal erosion model. And then we need another important thing, which is to translate the results of the hazard into relationships that relate the hazards with the damage at the receptors. So the damage at the infrastructures. And this can be done by using damage curves, for instance, for velocities, for flow velocities. Can be done as well by defining to which extent coastal erosion will promote the collapse of a building, for instance. And having these, we can construct our impact model and the impact result, and then to produce the risk maps. So this is the basic flow, let's say, of a model train from the very beginning to the end to have the risk maps. We can use this, as I told, as an early warning system. If we do it when we know the predictions of the storm, and we can upgrade as the forecast improves. We can use this as a decision support system, namely to assess disaster risk reduction measures. And we can also include here climate change scenarios, and then we change the modeling in order to already account for those climate change scenarios and test the risk reduction measures, taking into consideration the climate change scenarios. Well, the main question here is that so far, we don't have at the global level, of course, often the modeling of the risk reduction measures. So we often do not have, we have the production of models in several places, we have the test of models in several places, and then only rarely we have the testing of the potential measures also incorporated in the model in order to predict what can happen in the future. So we have the need to increase that, and we have the need also to increase the climate change effects on those modelings and on the behavior of these measurements. So there is the need to compute storm impacts with and without disaster risk reduction in place, and then to assess current and future disaster risk reduction measures effectiveness. Here, what I have is a very simple representation of a hypothetical triangular shape for a storm and for the associated storm surge, and then several variations of tide that we can include in order to model a given storm. And of course, we can do it for the current profile, which is here in black, or you can then change the morphology, inputting a nourished profile and test this measure in terms of reduction of the hazard at this coastal area. We can also, of course, include here a new level above the tide, which will represent, for instance, sea level rise, and we can again model the measure, which is the beach nourishment here, in order to see if it would be also effective or not after sea level rise, or if we increase the storminess, we increase, for instance, the wave height. So there is a huge amount of possibilities to work with the models and with the measures in order to test them. I'm going to talk on two different types of measures that can be incorporated on this approach. There is a third one that I'm not expressing here today. You can see a little bit more on this type of measures at this paper, Jager et al. 2018. So Jager and co-authors, they split into exposure reducing measures. These ones move the receptors, like house relocation, which is here placed, for instance. And for those cases, the model, if doesn't shift the morphology, needs to be rerun. So we run the model for the current conditions, for instance, and then to test the disaster risk reduction measure, the hazard will be the same, the consequence will be different because we shift the receptor, we didn't shift the hazard. The other one is the pathway obstructing measure. The pathway obstructing measure is, for instance, a beach nourishment. And there we have a change on the morphology. In these cases, we need to rerun the model because we changed the morphology. And because we changed the morphology, our hazard is going to change. Not, in this case, not the receptor. The receptor will be in the same place, but the hazard will not be exactly the same as it was before. There is a third one that I'm not going to go here today because our models are still not good enough for that, which is to know how the risk reduces by, for instance, education, by risk perception. And so that is not so tangible for our models, and but it's another disaster risk reduction measure, which is to communicate, educate, provide risk awareness, and then educate people on the behavior when facing the risk. But of course, that's a little bit out of the scope of these models, and so I will keep today just the discussion on these two: the exposure reducing measures and the pathway obstructing measures. And I made here a kind of a graph on what we need to do from the very beginning till the end for each of those. So for the exposure reduction measures, like the house relocation, and for the other one as well, we need to have a good model validation and good model calibration in order to assess the risk for current conditions. To assess the risk for current conditions, we need the current drivers, so sea level, storm surge, wave height, and the current morphology, of course. Then we can assess the effect of disaster risk reduction measure, still using the same drivers and the current morphology, because we just shift the location of the receptor. We can immediately know how it was the reduction on the provided by the measure. If we include climate change, in this case, we update the drivers. So if we include climate change on the assessment, we need to include sea level rise, we need to include change on wave height, and if we update upgrade the drivers, then we need to have a rerun of the models. Okay, for the pathway obstructing measure, since we are immediately changing the morphology, in this case, to compare the effect of the risk reduction measure with the current conditions, we need always to run again the model. So we have current drivers, but we have upgraded morphology. So there is the need of rerunning the models and compare the final results with the current conditions. Then, of course, if we include climate change, we upgrade the drivers and we upgrade the morphology. So again, we need to rerun the models to assess the effectiveness of the disaster risk reduction measures. After this sequence, for all of them, we need to have the effectiveness assessment. And mostly here, I'm talking on the risk reduction effectiveness. I'm not talking on the cost effectiveness and also not talking about acceptability, but these are quite important. Of course, for instance, we can have a very nice measure that completely reduces the risk, but if it is not cost effective, if for instance it costs 200 million euros for a small area, no one is going to implement it by lack of money. So it can be 100% effective in terms of reducing the risk, but not acceptable in terms of cost. It can also be not acceptable, for instance, in terms of social, cultural, or ecological issues. Namely, the social, cultural ones are quite important. For instance, on fishing village, if you define that the best solution is to remove the houses and to relocate the houses, probably the risk is completely avoided, but it's not going to be accepted by the population. And we had that example exactly here at Ria Formosa, a Barrier Island system, where the people did not want to leave their houses, and so they accepted the risk and they preferred to leave knowing that they have risk rather than going to other place. So I'm only talking again on the first part, which is the risk reduction. I'm not talking so much on the cost, neither on the social cultural aspects. To assess the effectiveness of a measure, we can something as simple as this formulation. So the percentage of the damage caused by the current situation by a given storm minus the damage caused with the disaster risk reduction measure in place for the same storm, dividing by the percentage of damage for the current situation. And this multiplied by 100 give us values in percentage, of course. A 0 means that there was no benefit at all on using the disaster risk reduction measure, like a beach nourishment, for instance, when compared to the current situation. 100% will indicate a total risk prevention by the model measure. So this is a very simple approach that we can use after modeling both situations. So let's go to examples of application of what I've been talking about to put it a little bit more obvious to the Faro Beach. And the study site is a barrier peninsula. In this case, it's not an island because it's attached. Is the western end of this barrier island system that we have just nearby Faro. We have an intensive human occupation, as you can see here, by the car parking, by all these houses, by the roads at this area. It's a very narrow barrier island. In this spot, for instance, this area of dunes is just 50 meters. And there is houses a little bit all over. Our wave regime is low to moderate energy. The average wave height here is around 1 meter. But we do have storms every year. We consider a storm when we have significant wave heights above 2.5, 3 meters, and they can reach up to 6, 7 meters. Well, a little bit more for the largest ones. We have a tidal range up to 3.5 meters, and storm surge is not very big. It's normally lower than 1 meter, and only rarely goes to values near 1 meter. Nevertheless, the storms have a relatively high energy, and they can promote impacts like you see over here, overwash, and also strong erosion with damage to structures, to houses, to restaurants, to infrastructures. And that happens quite commonly. I have here image from the 90s, but if I would put here image from 2002, it would be the same. 2010 would be the same. 2018 would be the same. So we have it all the time. The occupation is really until the border of the beach, as you can see. So the beach starts over there, the car parking is just over there. The same for the roads, the same for the houses. And so we do have road collapse, we do have houses collapsing from time to time. Our model train for Faro Beach, and this was built during the risc-kit project, is now we are rebuilding it, in fact, for another project. We have, let's say, a broader model using Delft 3D and Swan that comes from the Atlantic to the Gulf of Cadiz. Then the generated water level and wave spectrum goes to a more detailed model for the Ria Formosa, and then the water level, the driver's water level and wave spectra go to the X beach, applied only to the Faro Beach. And from the X beach, we get the erosion and the overwash, and all the data of all the runs that we made so far are kept on a Bayesian network. So we can assess the data and we can assess all the predictions we had before when we need. And this was mainly done for the early warning system developed during the risc-kit project. We are now redeveloping this early warning system and extending to another 2 beaches in Portugal. So these are kind of image of the larger scale data that then goes to the Gulf of Cadiz grid, then goes to the Ria Formosa grid, and then for this one is already the X beach working and producing the final results. The disaster risk reduction measures that we modeled for this area, so we modeled current conditions and we model disaster risk reduction measures, we select them from the existing coastal management plan. So we decided not to create anything new. We decided to go to the coastal management plan and what it was pointed out there, and to test it and to incorporate those. So we had beach nourishment, which is a pathway obstruction measure, which requires immediately extra modeling. And this is the original profile and then the nourished profile that you can see represented here. So it's a beach nourishment with about 40, 50 meters wide. And then we have house removal. House removal from these 2 zones, zone 1 and zone 3, so the yellow and the green. It's something that was planned for the Praia de Faro. As I told you, it was not achieved for this area, mainly because the population didn't accept it at all. There were only some other areas to the west and to the east of this area where a large number of houses have been removed, but not these ones. In fact, they are still there. But we tested anyway because it's something that exists on the coastal management plan and maybe in the future will be implemented or not, don't know. So then we needed to do that connection between the hazard model and the impact assessment that I told you before. And that connection, in our case, we define for the hazards of overwash and erosion promoted by storms. We define that if our discharge is smaller than, the model discharge is smaller than 1 square meter per second, would be safe. The infrastructures would not be damaged. If the discharge is between 1 and 3 square meters per second, so we assume that our structures can have some sort of damage, can be potentially damaged, but not fully damaged. And if they are, this is based on literature, it's not on our own. And if the overwash discharge is really quite big, then our infrastructures will be fully damaged. So this was what we assumed. For instance, this can be applied, and we are applying this now for life damage. So for people, that sometimes, unfortunately, go to see the overwashes and go to see the overtoppings. And so now we are adapting these values, and they are much smaller for threat to life. So we are adapting these values now, not only for infrastructures, but also to threat to life. For the house destruction and infrastructure destruction by vertical erosion, so the formation of beach scarps and dune scarps, it's a little bit more complex, but basically I'll synthesize like this. We define two buffers around the houses. If our beach scarp doesn't go to the buffer, it's far away from any of those buffers, the house is considered safe. If, for instance, the first buffer is already having a beach scarp, more than 1 meter beach scarp, we consider potentially damaged. Why? Because the dune can collapse, and if the dune collapses, maybe the building will also collapse. If the beach scarp goes to the 5 meters buffer, then we consider that the house, or below the house, we consider that the house is fully damaged. These houses, they are on top of the dunes. Okay, so they are just sitting on top of the dunes. If you have a scarp on the dune, they will fall down. And we already saw that in the past. So our assumptions were based a little bit on what we saw, and we defined these buffers also as a security, let's say, if we have a beach scarp going on the yellow, we still say that it is potentially damaged, even if it doesn't goes to the house. So that was our definition to translate hazards into risks and to promote impact assessment. Well, let's go to the results. I'm starting with the with the storm with the return period around 50 years. It is a storm that I have it here higher than 7 meters. In fact, is almost 8 meters, and a peak period of almost 15 seconds. So this is a storm with a return period of 50 years for this area. And for the current conditions, this is what would have in terms of overwash, the flow velocities. You can see these areas and the flow velocity is estimated for these areas. We know that these are the worst areas. This is the car parking. We know this completely. We also know this one is a very strong area of overwash. And for this storm, we would have about 80% of the houses safe, about 18% of them potentially damaged, and 3% would be probably completely damaged. So what happens if we put in place the nourishment? So if we put in place the nourishment, this is the overwash still would occur, but as you can see, with much lower velocities, much lower discharge. And so the safe would increase from 79 to 92%. The damage would be probably 0, and the potentially damage would reduce from 18 to 8%. So we can already compute the values using that formula that I showed previously to know the effectiveness of the nourishment. It would not be total, but it would be effective in some way. Let's go to the erosion. So the other one was overwash. This one is erosion. On the erosion, what you see here in red is the areas where we have a strong vertical displacement. And the important part here is this black line. This black line is the contact between the infrastructures and the beach. So if you have red after the black line, it means that the infrastructure is going to be destroyed because you have a scarp, you have a beach scarp, okay? So every time that you have red crossing the black line, it means a strong beach scarp, and your house is going to be destroyed. And of course, you need still to account with 10 meters buffer zone to potentially damage. So we have here for this storm, 50% of the houses would be safe, 5% of the houses would be damaged according to our expectations, or to these used assumptions, and 45% would be potentially damaged. If we include the nourishment, obviously you can see that the most of the strong erosion displaces toward the sea, and the only 2% of the houses would be potentially damaged. So this means that we reduced the risk from 50% of houses being damaged or potentially damaged just to 2%, which means a 96% of effectiveness using the nourishment. Okay, so we can assess the nourishment, and we can know that the nourishment here would have a 96% of effectiveness. Of course, all of us know that the nourishment only has its shape on the very beginning. After a few years, the sand is not there anymore. It starts to be transported, and so of course this is made for the nourishment immediately after being located over there. But we can't see doing any more modeling for how many years the nourishment would be effective and how this would evolve in time. Here we have the house removal. So in this case, we didn't rerun the model, we just took out the houses. So the blank area represents the place where the houses would be removed. And of course, there is a direct reduction of the potential consequences. But because we didn't shift the morphology at all, we just removed the houses, the overwash level would be the same. The overwash intensity would be the same. In fact, still some houses here on the back barrier would be affected, and so the reduction of the risk would not be so effective as by placing the beach nourishment. The same for the erosion. We remove the houses on the yellow part, but we still have here, for instance, some houses that would be damaged. We still have here some houses that would be potentially damaged, and so we do have a reduction, but still would not eliminate all the risk at the area by removing these houses on this yellow part. If we place together the nourishment and the house removal, which we can also analyze, of course, then we go to a measure that is basically 100% effective, both for overwash and for erosion. So we have residual values of risk at the end. But here we have that problem that I told you on the beginning. This measure just for Faro Beach is estimated to cost between 100 and 200 million euros. So it's effective in terms of risk reduction, but probably not easy to be put into place due to the high cost. And more than that, people also do not accept so easily to be relocated. Then we had 2 years ago the opportunity of not only testing these to an hypothetical storm of that will occur in each 50 years, but we did have a strong storm called Emma storm that hit the area between 28 February and 3 March of 2018. And it is an interesting storm because you have Emma here, the track of Emma in red. You have the track of Cynthia that I just told you, that was one of the most devastating ones in Europe in the last years. And you have also the track of the 1941 called cyclone that was the most devastating in the Iberian Peninsula, that killed 1,500 people in the Iberian Peninsula, mostly by winds and not so much by coastal floods, but also was devastating on coastal areas. All of them have a very, very similar storm track. So we know that we have storms with a strong impact on this area coming from the southwest. This storm had a maximum wave height that was almost 7 meters, with an estimated return period around 16, 20 years for the wave height, a peak period of 13 seconds. And then it was during spring tides with a 60 centimeter storm surge. So a total water level of 2.1 meters above mean sea level was reached, which also has a return period of 6 years just for the total water level. So I don't know what is the combination of these two return periods, but for sure it's more than 20 years, 25 years or something like. So it was a relatively strong storm hitting the area. It promoted strong erosion. You can see here the profiles that we made before and after. We had removal of 2-3 meters of sand in all the entire area. We had large overwashed areas all over. We had shoreline retreat in some places. And of course, we also had the damage of the car parking, the promenades, stairs, threatening of houses, some people being relocated during these days, and so on, so on. So it was already a relatively strong storm with some level of destruction on the area. So we could test our models in a real storm and test again what would be the effect of these coastal management measures if they would be in place. So again, we went back to the nourishment that I told you and to the removal of the houses that I told you, and we applied as well this simple equation to assess the effectiveness on risk reduction. So if we'd have either nourishment or house removal for the overwash promoted by this storm, any of those measures would be 100% effective on avoiding damage or potential damage. So either house removal or nourishment for this storm would have an effectiveness of 100% for this storm. For the erosion, it's not exactly the same, but if we had had just house removal, it would be 100% effective for damage, but only 54% effective for potential damage at infrastructures. The nourishment would be 100% effective for damage and 77% for potential damage, and the joint use of nourishment house removal would be 100% for damage and 83% effective for potential damage. So we see that for what we call damage of infrastructures, any of the measures would be effective. So no structures would be damaged if this coastal measures would be in place. Nevertheless, because we have some safety rule, let's say, there is some level of potential damage that still would exist, but as you can see, they would be also strongly reduced by the existence mostly of the nourishment, but also by the house removal. So we could assess the effectiveness of those coastal management measures at the area for a storm that really hit the area and that had consequence at the area. Well, we can, taking all this into consideration, doing a lot of modeling, we can also define and use this approach to define a time frame for implementation of the coastal management measures. For instance, we can perform ex ante all the disaster risk reduction measures that we have years, decades before, as we are doing now, and we can include climate change on top of the equation. So we can change the drivers and rise up the waves or rise up the sea level according to what we have in each area of the globe. And then, of course, with time, we can make a reanalysis according to new data and information. With this, what can we do? We can define at which time the measure should be implemented at each region to optimize resources. Probably in several regions, we do not have the need of a beach nourishment today, but with the expectation of sea level rise and the expectation of increasing of storminess, maybe we will need it in 10 years. So we can model again, when do we need to implement these coastal management approaches. And so we can define a time frame for coastal management today. Probably will not be the most correct one, because we only have predictions, but with time, after 5 years, we can again do a reanalysis of these and readjust our time frame. And so we'll have the conditions for the current situation. We'll have when should we need the first measurement, like a beach nourishment, for instance, when should we apply the second measure, like a dune recovery, and when should we apply a third or fourth measurement, and when we need to do a second beach renourishment, etc., etc. So we can get a time frame for coastal management next 50 years, 100 years, run these models, implement the coastal management measures, the most effective ones, and define at which time they should be placed in order to avoid risk. And this is something that we should start to do in order to improve our coastal management plans. Well, of course, there are still a lot of limitations and future developments to be done for these decision support systems. One of them is the modeling limitations. We still have a lack of quality data, field data for most regions. We do have areas in the world that have been very well studied, but doesn't mean that all the areas have been. And even on those, we have, for instance, lack of data on water discharge. It's relatively difficult to measure. Inundation extents, for instance, amount of shoreline retreat induced by storms. And this is quite important because these models, and particularly in this case XBeach, they need local model calibration validation against data. If you don't have these, the application is limited. We do need to calibrate and validate our models for each area in order to be sure that our results are true or near to reality. There is also difficulty on the direct use of models by stakeholders. Not, well, I would say that only a reduced number of coastal managers will be able to use these kind of models. And thus we need to translate these models into tools that can be easy to play by the coastal managers. And here, systems like the Bayesian networks or any other approaches that store all the information and then, for instance, translate it in WebGIS can be easy for a stakeholder to play with the results, because they are not going to run the models, but they want to play with the results to know what is the best for them. We also need to define better the relationships between the hazard indicators and the exposed elements. For instance, most of the damage curves that we have been developed for continental floods. So the damage curves relate water velocity from a flood with the stability of buildings. We don't have damage curves for overtopping, for instance. We need to start to have those. We need to start to have these limits when kind of a building made on concrete or made on wood or whatever is going to be destroyed by flow velocity. What is the limits of the building to collapse? What are the limits to threat to life as well for instance, by overtopping again? These already exist, but they need to be improved. We need to extend the effectiveness analysis to the economic, to the ecosystem, and to the social cultural aspects, because at the end, this will be as important as the risk effectiveness that I've been talking about for any coastal manager. Coastal managers will not take the decision only based on the risk analysis. They will take decision also based on the economic values, on ecosystem values in some cases, and also on social cultural aspects as well. And something that is not also still completely provided by the models and by the analysis that we have is the cascade effects. So when we model, for instance, the implementation of beach nourishment, we often model on these projects just what happens on that area. We kind of forget what is going to happen on 2 kilometers away or 3 kilometers away. It might be positive even, or in some cases, in some measures, it might be negative. So we need to define the cascade effects as well on this modeling, and also to define the economical cascade effects that result from the implementation of these measures at medium to long term. As a final remarks, well, I showed here, I proposed a kind of decision support system to test the adaptation and risk reduction measures that can consider climate change and can be enough to include the definition of a coastal management into a time frame. I also propose a simple effectiveness assessment index to evaluate the model result for each risk reduction measure. And this decision support system can be used as a planning tool to define the impact of management actions, including climate change at the coast. And in our case, it proved to be useful to Praia de Faro. For the risk analysis of Praia de Faro, we passed all this information to the coastal management, and the coastal manager at the end didn't do much so far, but let's see if with all this information in the future, the risk at Faro Beach can be reduced. And it's all. Thank you so much.
Thank you, Oscar. That was really good. Thank you.
Thank you very much, Oscar. Yeah.
You're welcome.
Yeah, it is 2 now, so I think we will have time for some questions that Kristen will take. But I just want to jump in and just have one question before. There is like the photos of the damage of Praia de Faro. They look the same since the late 90s, and so when I was there, well, I was thinking that wasn't last very long, and that was going to go in the next storm, and so on. So what's happening? Is it more resilient? Have there been any measures implemented?
No, the positive point here is that updrift, since 96, 97, we had 3 or 4 big beach nourishments already with more than 2 million cubic meters of sand. So immediately updrift. So it means that in fact, Faro Beach is being fed by beach nourishment, indirectly fed by beach nourishment. So it became a little bit more resistant than it was in the 90s because there is sediment source, artificial one, but there is.
Giovanni, you almost look like you're about to ask a question. Did you want to?
I think we can go ahead with the ones that we have, but I do have some questions.
Sure, yeah. You look like you're going to jump into the screen almost from here. It's very exciting. Thank you very much, Oscar. That was really interesting to hear all about what is going on with your group. So we've got a couple of questions that are popping up in our chat. So I'll read them out to you, and hopefully you can give an answer. So Mandy Tran asked the first question here, and she said, "Hi Oscar, you mentioned that you were redeveloping the early warning system for 2 other sites in Portugal. Are you significantly updating your approach from the approach that was developed during your risc-kit, and which includes the overall structure of the process-based models, consequences in the Bayesian network, or are you adding more into it?"
We are adding a little bit more, but the basic is the same. What we are adding more is that we are including areas with seawalls and artificial structures. So far the model only had application to sandy beaches, and now we're going to use it to areas with severe protection, like on the west coast of Portugal. and then we'll include it on a web open early warning system that already exists for one beach in Portugal. It was developed by colleagues from Lisbon, and we're going to include these 3 beaches in that system as well. So those are the new parts. It's including seawalls, so overtopping and risk on seawalls as well, and then really make it available to everyone through a web system.
Cool, thank you. And the next question I've got here is from Hajing Yulu. He says, many thanks, Oscar. So he has 2 questions. So the first is, how do you set up the relation between the hydrodynamic features, water depth, flow velocity, or discharge with the damage level? Maybe I'll let you answer that one first if you want, and then I'll ask the second one.
Yeah, it can be in different ways. For instance, you can use those damage curves that I told you. We are not available for all the places. Even here in Portugal, they didn't exist. They don't exist, and we adapted some from other places. Or you can then go and go to a simple approach like we did. If the discharge is less than 1 square meter per second is safe to the infrastructure. If it is more than 3 square meters per second, the infrastructure is going to be damaged. And if it is in the middle, we don't know. So we define potentially damaged. And this was based on these damage curves. So these limits were defined based on these damage curves.
Cool, thank you. So the second question was, do you consider the shielding effect in your model? So based on the field surveys, buildings at the rear would be efficiently or could be efficiently protected by the ones in front of them by this. Is that part of the model?
No, it was not included. Nevertheless, if you want to increase the complexity, you can place some rigid parts at the model. You can include rigid morphology, let's say, at the model and remodel again. But no, it was not included.
Cool. This next question is a UNSW colleague because it's their ZID, and I can tell it's Ron by looking at his picture. So Ron Cox is asking about, have the local Faro Beach community indicated what they consider to be acceptable, as in what is the probability of failure damage over a nominated period, say 10 years?
No, not in that way, not in that way. And also the communication between the managers and the community was not great, let's say, from the beginning. So the community saw the plan and didn't really like it. In fact, the community, what they would like to have would be just seawalls and groins. So it was a quite different approach from the coastal managers and the community. So far, not much was done, except the removal of second houses that were not being used, let's say, or they're just used for summer holidays on the sides of this area that I show. So there is still a lot to do in terms of connecting the community to the coastal management and try to find a solution that is acceptable to all.
Thank you. The next question is from Emily Lane, and she's asking about how much of the beach nourishment is eroded away by a 1 in 50 year storm. And then have you also considered having back-to-back sort of 1 in 50 year storms in quick succession?
Yeah, almost all of it. It would be really too near the dune. So, or in some cases, 5-10 meters of berm would still be in place. We didn't made a storm succession analysis. We are doing that now, not with 2 1 to 50 year storms in a row, but we are considering now, and we are running now a few storm groups.
Cool. So the next question is from Giovanni, and maybe Anna sort of added on to this one, saying, but the approach relies heavily on morphodynamic modeling. And so do you consider in any way the uncertainty that's associated with the limited predictive skills of these models? And Anna's added, in fact, it's 4 models. And so do you consider all those models and their probability.
Yeah, no, not in these cases of the ones that I show. We validate them against most all the data that we had. We calibrate them as well. On this new project that we have, we had more data. We recalibrated the X-speech again, and now we also have some knowledge of the uncertainty associated to the X-speech on this new project that we are running now. But the results are still yet to come, let's say. On the previous one, we didn't. But we calibrated as far and as much as we could in order to minimize the errors, let's say.
And the next question we have down here, it's the last one so far we have, is, hi Oscar, from James Carley. What is the reason for the community's preference for seawalls that you mentioned, is it not accepted, or a combination of seawalls and nourishment?
Well, the community, basically, they are a little bit, well, I would say self-centered in the way that they want to protect just their houses. They don't really care much about the beach value or the aesthetics. And thus they prefer to have their houses over there, even if protected with seawalls. And I think that what is going to now is trying to avoid the seawalls, because we are in a natural park, of course, and to use nourishment in the future. But then here we have a lot of well, things in place. The national managers only give money to the nourishment if some of the houses are relocated. And the local ones want just the nourishment and not to relocate the houses, because if not, they will lose the community and they will lose the votes. So the result is there is no management in place.
I had one last question, and no one else does. It had to do with you talking about doing future scenarios as well with sea level rise, and back to what Giovanni asked about, the uncertainties in morphodynamic models. What's your opinion on how do you run something like X-speech with sea level rise in 50 years from now, when we know that the morphodynamics would have changed in that time anyways?
Well, there's a lot to analyze on that, because, for instance, if you just consider sea level rise, and if you admit that your area has enough sediment to keep the pace, you don't even need to run it, because supposedly the morphology will rise up as well in the same way as the sea level rise will rise up. However, in places like Faro Beach, where we do have rigid structures that will not rise up, because they will be the same at the same level, then you can do that. Then you can do that exercise. You can kind of maintain a relatively similar morphology to the one we have today, and start to rise up your sea level, and to model what are the potential consequences for the future. Of course, we'll always have a high level of uncertainty. That's why I stated that the results that we have should be reanalyzed from time to time with new data and new information. And that's also important. It's important to have a time frame for the future, but it's also important to know that that time frame will be improved in the future with new data, new information, and better modeling.
Thanks very much. Well, that's the end of all the questions that we have here. There's also been a number of people just to say thank you for the wonderful talk here. But Anna, do you have anything else that you wanted to add?
Just emphasizing, thank you very much for waking up at this ridiculous time in the morning, Oscar, on a holiday. Thank you very much. And
You're welcome.
We are all super helpful, super grateful that you did that for us. It's been a great.
Thank you.
So thank you.
Thank you for the invitation, and I'm probably going back to bed. So see you guys.
Thank you very much.
Bye-bye.
Bye-bye.
Bye.
Bye.
Thanks, Oscar.
He's gone already.
Yeah, I would too.
Yeah, I mean, I'm amazed he got up.
I am amazed he said yes.
And I think Kristen was also running somewhere probably because she's already disappeared.
Ah, probably. Yeah. Is he teaching today, Mitch? Do you know?
Kristen,
Yeah.
tomorrow.
No.
Yeah.
Okay, I think I go.
Wait, I'm going to stop.